So we're going to start recording again, and we're going to look at a different way to think about metabolic pathways. So we're going to look at two types of things here. We're going to look at something called oxidation reduction reactions, and we're going to look at anabolism and catabolism. Now think about metabolism. Anabolism and catabolism are really the two kind of subdivisions of metabolism. And your body is always carrying out both of these reactions. So before we get to that, let's look at one of the main types of reactions that occurs in anabolism and catabolism. We've already talked about chemical reactions as being exergonic or endergonic. But what we want to talk about now is something called a redox reaction. And redox is short for oxidation reduction reactions. I'm not sure why in the abbreviation they always write the re from reduction first, but they do. And in redox reactions, there's always a transfer of electrons. Something gains electrons, something loses electrons. So let's look at this graphic. We have a chemical represented by the yellow A and another chemical represented by the purple B. And then this pink represents one of the electrons in chemical A. And in this chemical reaction, the electron that started out in chemical A ends up in chemical B. When we have something that loses an electron, so this yellow chemical, we say that A is being oxidized. This is called oxidation, and oxidation is always the loss of electrons. When we have something like this purple B that gains an electron in a reaction, reduction is gaining an electron and B is being reduced. So notice when we talk about something being oxidized or reduced, we're talking about this as the change that occurs from when they were a reactant to when they were a product. Now, in chemistry, oxidation reduction reactions happen in a lot of different ways. But oxidation and reduction are basically the reverse. In this example, A lost an electron, B gained an electron. So when we look at a reaction where we have oxidation happening, we have to have reduction happening too. We can't have oxidation happening without reduction. Think of it like a sports game. If one team wins, the other team loses. We can't have something that's oxidized unless something else is reduced. So we want to keep that in mind. Now in chemistry, there are lots of oxidation reduction equations. But when we look at biological systems, it's almost always something where we gain or lose bonds to either hydrogen or oxygen. So we're going to focus on that. Keep in mind while we're focusing on that, if you would take a chemistry class, you would look at this from a much broader perspective. So when we look at a living system, oxidation occurs when a reactant gains bonds to oxygen atoms, or when it loses bonds to hydrogen. So either one of these, they could both happen or just one happens. But if we have a reactant and at the end it has another bond to oxygen that it didn't have before, or if it lost a bond to hydrogen that it had before, then we're going to say that it's oxidized. Reduction is the opposite. So reduction is going to happen when we have a reactant and it gains a bond to hydrogen, or when it loses a bond to oxygen. And again, both of these might happen, or maybe just one. So let's look at an example of this. Let's take CH4, which is an organic compound. We know that it's based on carbon. And this is a compound called methane. And what we're going to do is we're going to take this methane and we're going to burn it. Methane is one of the things that's found in natural gas. So if we burn this, if we put it in natural gas, if we put this natural gas in oxygen, we're going to end up making some carbon dioxide and some water. And there should be 1 plus there, not 2. So let's think about the carbon atom here. We know that carbon needs 4 bonds. So carbon starts out with bonds to 4 hydrogen atoms. It ends up with 4 bonds to 2 oxygens. So carbon has lost some bonds to hydrogen. It's gained some bonds to oxygen. So if we go back to our definition, if we're gaining bonds to oxygen and losing bonds to hydrogen, okay, so carbon is being oxidized. If we look at hydrogen, these hydrogen atoms each have a bond to carbon. At the end, the hydrogen atoms have a bond to oxygen. So if we think about these hydrogen atoms have gained a bond to oxygen. Now they didn't lose a bond to hydrogen, but they did gain a bond to oxygen. So these hydrogen atoms are being oxidized. So we could just say that methane is being oxidized because the carbon in it is being oxidized, the hydrogen in it is being oxidized. Now, if we look at O2, at oxygen gas, oxygen atoms need 2 bonds. So when we have a formula of O2, the 2 oxygen atoms have a double bond with each other. So oxygen starts out with 2 bonds to oxygen. At the end, oxygen either has bonds to carbon or it has bonds to hydrogen. So oxygen is actually losing bonds to oxygen. So that means that if we have something that loses a bond to oxygen, it's being reduced. So here we could say CH4 is being oxidized, O2 is being reduced. So if we have oxidation happening, reduction has to happen too. We can't have just one of them. So we want to keep that in mind. Now let's go back to metabolism and think about the 2 different branches of metabolism. When we're looking at endergonic reactions or exergonic reactions or oxidation reduction reactions, or there are a few other types, remember that whenever we talk about metabolism, metabolism is just the totality of all these chemical reactions happening in living cells. And there are 2 types of pathways. So let's keep these arrows in mind. So if our reactants are these 4 little purplish dots up here, and we add some energy, okay, so notice we're adding energy to reactants. So this is going to be what? An endergonic or endothermic reaction. We're going to use that energy to stick these 4 small atoms together into a big molecule. This is an anabolic reaction, or this is an example of anabolism. When we think about anabolism or anabolic reactions, they involve taking small molecules and combining them into bigger molecules. Now, when we build a bigger molecule, we're making chemical bonds. So remember, chemical bonds store energy. So if we're going to build some bonds, we need some free energy. We have to add some energy. So these are going to be endergonic or endothermic reactions. The products, this blue chain of 4 atoms down here, is going to be higher on our graph than our 4 separate atoms. And how do cells build bigger molecules? Well, almost always through a dehydration synthesis reaction. So when we think about endothermic reactions, we want to keep 3 things in mind, or anabolic reactions, we want to keep 3 things in mind. we're going to build bigger molecules. They're going to be endothermic, and they're going to be dehydration synthesis reactions. So that's this arrow over here on the right side of this graphic, because we're taking what's at the top and we're converting it to what's at the bottom. Now let's think about starting with a big molecule like this chain of 4 atoms, and following this arrow, let's break it down to a small molecule. If we do this, this is something called catabolism or catabolic reactions. And they always involve taking large molecules, breaking them down to smaller ones. And when we do that, so if we start out with these 4 atoms put together, we break it down to 4 separate atoms, that's going to release some energy. So this is going to be an exergonic or an exothermic reaction. And if you think about what we talked about a few days ago, this is going to be a hydrolysis reaction. So when we think about catabolism, it's going to be big molecules to small molecules. We're going to be breaking molecules down. It's going to be exergonic or exothermic. We're going to release energy because we're breaking bonds and energy is stored in chemical bonds. And it's going to not just take big molecules, break them down, release energy, but it's going to be a hydrolysis reaction. So when we think about the 2 types of reactions, we want to keep these in mind. Now notice, you can have oxidation reduction reactions, and they can happen in anabolic pathways or catabolic pathways. And individual reactions in a pathway can be oxidation reduction, they can be endergonic, they can be exergonic or endogonic. But here's what we have to keep in mind. Overall, an anabolic pathway will be endergonic. Overall, a catabolic pathway will be exergonic. So there might be an individual reaction that's endergonic, but if it's a metabolic pathway that's catabolic, it will always be exergonic. So keep individual reactions separate from pathways. When we look at a pathway, anabolic pathways always absorb energy. They're endergonic or endothermic. Catabolic pathways always release energy. So they're exergonic or exothermic. Doesn't mean every reaction in one of them is either endothermic or exothermic. It just means overall. So keep individual reactions separate from the idea of the whole pathway. Any questions about pathways or enzymes before we leave for today? No? Okay, I'm going to stop recording and I'll let you